Okay, so in this video, I'm going to summarize Newton's laws. All right, so as you can see, number one, what we here is we have Newton's first law: the sum of the forces equals zero, and so this is when the object is not accelerating. So an object could have a lot of forces acting on it, but if the sum of those forces is zero, then that means the object is not accelerating. Okay? Yes, so you may wonder, does it mean so it's not moving? No, it can still be moving. The object can still be moving. It still can have a velocity, but it just can't be accelerating. Okay? So again, if the forces are, let's call it balanced, if the forces are all balanced, and then therefore that their sum is zero, the object is not accelerating. Okay? So that's the first law. Second law says, what if the sum of the forces are not balanced? What if they're imbalanced? So in that case is here, that means if you add them all up, if there's a non-zero answer like 5 or 8 or whatever, then so the forces are imbalanced. Therefore there is an acceleration. Okay, and so what this says here is, whatever the acceleration is, let's say it's 3 meters per second squared. If you multiply that times the mass of the object, maybe it's 10 kilograms, that gives you the force in newtons. So this relationship just tells you there's a direct relationship between force, mass, and acceleration. Okay? So once again, the first law basically says if the forces are balanced, it's not going to accelerate. But the second law basically says if the forces are imbalanced on the object, then it is going to accelerate. Okay? Now, now here on the number 3, I just want to make a point. The first and second laws, in order to use them, you have to be in what's known as an inertial reference frame. Inertial means non-accelerating. So yes, it can still be moving. It can still have a velocity, but just it can't be accelerating. So if you're looking at a ball, like I have this ball, for example, and I want to compare it to the Earth, well, technically, of course, the Earth is accelerating because it's moving in a circle. But we count the Earth as an inertial reference frame, as a non-accelerating reference frame. But if you had this ball and you wanted to analyze it using Newton's first or second law, and you were inside of an accelerating car, for example, you couldn't, because the reference frame there is accelerating. So when you're analyzing something, you have to ask, what's your reference frame? Is the reference frame accelerating, or is it not accelerating? And if it's accelerating, you can't use it. Now, which brings me to point number 4. If you happen to have an object that you do want to analyze using Newton's first or second laws, and it happens to be in an accelerating reference frame, let's say an automobile, what you need to do is you need to introduce fictitious or pseudo forces. What that'll do is that will counteract the accelerating reference frame or the non-inertial reference frame. It'll counteract it to essentially put you in an inertial reference frame. Okay, so what we have here is we have a car. It's accelerating at the top. We have a car that's accelerating, and there's some block, for example, that I want to analyze its behavior. I want to analyze the forces acting upon it. But the car is accelerating, so therefore the car is in a non-inertial reference frame because it's accelerating. So what I could do, though, is I could add some fake, pseudo, or fictitious forces to the block that counteracts the acceleration of the reference frame. And what that'll do then is that will allow you then to actually analyze the block using Newton's first or second laws, because you've counteracted the accelerating reference frame. So if you do that, then it just works. So you can actually use Newton's first and second laws in an accelerating reference frame. The only thing is you have to be sure to add those pseudo forces. But if your object or whatever is in an inertial reference frame, meaning it's not accelerating, then you can just analyze it normally, and you don't have to add any fictitious forces. Okay. Number 5, I want to talk about Newton's third law. Now, Newton's third law is about two objects that are that are interacting with each other. And so two objects that are interacting with each other will have equal and opposite forces. So for example, here we have a person, This person has a weight, which is gravity that's accelerating down. Gravity, which is like 9.8 meters per second squared, times its mass, 50 kilograms or whatever. So, and that'll be some force. So this person has a weight, which is a force, and which is in newtons, and so it's pulling the person down. You can see the arrows going down. But because the person is interacting with the floor is also pushing up. So if the person were pushing down with 100 newtons of force, the floor is also pushing up with 100 newtons of force. Okay, so therefore the two forces zero out because one is pushing down at 100, one's pushing up at 100. Therefore, the person is not moving, right? If for some reason he was pushing down at 100 and the floor was pushing up at, let's say, 20 newtons, well, then the forces are imbalanced, and guess what? Now the person's moving. Not only moving, he's accelerating, okay? So the reason this person is not accelerating down is because, yes, there is a force going down, but there's also a force coming back up. So the net of those two forces is zero, okay? And so that's Newton's third law, where you have equal and opposite forces. All right. And then lastly I'll talk about free body diagrams. Free body diagrams are just ways for you to analyze physics problems in complex scenarios. Now, when you want to construct these free body diagrams, you have to each diagram has to contain a single object. Like, you can't have 3 or 4 objects in a free body diagram. It has to be just one object per diagram. Next, you have to show the forces acting on the object. Don't show the forces don't show the forces of the object on something else, because we don't care about something else. We only care about the forces acting on this particular object, okay? Directly. And so what I have here is I have a picture of a person, a very badly drawn picture of a person, and this person is pushing a block to the right, okay? And so let me just do this. So here's a person here, and they're pushing this block to the right. Okay, so I've shown this person using a dot. The person is the dot. And then what I'm going to do is I'm going to show all the forces acting upon. Sorry. The dot here is the block, not the person. So yeah, the dot here is this block is the dot. All right. And so what are the forces acting upon the block? Well, so first of all, there's gravity, right? Gravity is affecting this block. How? It's pushing down, right? Or pulling down. It's pulling down on the object, and that's the weight right here. Let me just do this one, and so that's this one. So the weight, which is a force, is the mass of the block times gravity. Okay, so there's a force like pulling him down or pushing him down. Maybe it's pulling him down. Okay. But then there is a table, this block, or some sort of surface the block is on, and so there's another force, which is a normal force, acting upon this block. So this block has gravity pulling him down, and it has the normal force is pushing up. Okay, so that's this, and they're opposites. They're opposites in magnitude. So let's say the weight is 100 newtons. The normal force also has to be 100 newtons. If it wasn't the same, then that means the block would be accelerating in the up and down or the y direction, and it's not. It's not accelerating up or down. So the top and bottom forces have to be the same. And then the other forces, you can see there's a person pushing, right? There's a person pushing this block. Right, and so there's some sort of pushing force that's happening, and so because there's no other force in the opposite direction, that means that the block is going to actually move and or accelerate in the right direction. Okay, if there was another person on the other side, for example, if there's a person over here, and he was pushing in this direction, the same force as the other person, well then the block wouldn't move at all. But because there is no force pushing to the left, that means the block is going to accelerate to the right. Okay, So once again, this is just a free body diagram where you take the object, a single object in question, that's a dot, and then you put all the forces all around it that are acting on the object, and then from there you can figure out force, mass, acceleration, velocity, position. You can solve mostly any physics problem from that. All right. So anyway, that was it. That was a summary of Newton's laws.